So today we're going to be looking at double integrals in polar coordinates, and what we're going to do is we're going to do two questions, one of which is far easier to integrate using polar coordinates, and the other one which is far easier to integrate using Cartesian coordinates. And the point of this video is to show that sometimes one is better than the other. So the first question here is one which basically I don't know how to do in Cartesian coordinates. I'm not 100% sure it's possible, but in polar coordinates it's relatively easy, and the clues are because we got your x squared plus y squared here, and we got the square root of 1 minus x squared here, so it's clear that they want us to convert to polar coordinates. So just to recap, let's just draw ourselves a little diagram here, and we got if we just take this as being basically our theta here, and then r is here, and we take one of these little things here, let's take that one, basically this distance here will be dr, and this distance here will be r d theta, just because we are going along the arc, and therefore the area of that will be r d theta dr. And so basically, as a recap, dA, which is dx dy, which is dy dx, which is the area in Cartesian, basically is r dr d theta in polar, and you have to remember that because we will be converting it from one to the other. And the other thing that we need to know obviously is that x equals r cos theta, y equals r sine theta, and x squared plus y squared equals r squared, and that of course just comes from, if we draw here, here's any point x, y, and this distance is r, and that is theta, then obviously x is r cos theta and y is r sine theta. Okay, so what we got to do, let's have a look at the actual integral here. We first of all have to find out the region over which it is integrating. So if we look at this one here, which is the y, it is integrating from y, let's have a look, equals 0 down to the square root y equals minus root 1 minus x squared. Well, clearly that is x squared plus y squared equals 1. So if we draw the circle x squared plus y squared equals 1 here, where this point here is 1 and here is minus 1 on the x and 1 on the y, we are going on the y from minus 1 plus root x up to 0, and on the x we're going from 1 to minus 1. So clearly this is the area that we are integrating over, which is the bottom half of the unit circle. Now in polar coordinates, that would basically be r going from 0 to 1, so r would be greater than or equal to 1 and less than or equal, sorry, greater than or equal to 0, less than or equal to 1, and theta would go from pi to 2 pi, so theta will be greater than or equal to pi and less than or equal to 2 pi. So the limits on this are relatively simple, and here cos of x squared plus y squared, well, x squared plus y squared, we know, that's a very basic polar definition, is r squared. So we can rewrite this integral here as the integral, double integral, cos of r squared times, and now instead of dx dy, we're going to put r dr d theta, so cos of r squared times r dr d theta, and we know the limits now, and because we're integrating with r first, and that will be the limit between r equals 0 and 1, and then we will integrate over the theta between pi and 2 pi. Okay, so if we look, we have to integrate this bit here with respect to r first. Well, if we just look at the derivative of sine of r squared dr, that gives us cos of r squared times by the chain rule 2r, and so therefore we know that the integral of cos r squared r dr is going to be that over 2. So therefore we have 2 pi and pi. We can integrate this r bit now, which is going to be sine of r squared over 2 between 1 and 0 d theta, which equals the integral between pi and 2 pi of the sine of 1, just putting r equals 1 into here, over 2 d theta, which equals the sine of 1 over 2 times theta between 2 pi, and that is equal to pi over 2 sine of 1. And that is the answer to this integral, which is impossible in, or almost impossible in Cartesian coordinates, but it's actually relatively simple in polar coordinates. Okay, so that's a clear example of where an integral should be done using a conversion to polar coordinates. Okay, now what we're going to do is a little bit of fun. Question number 2. I'll just pause the video if anybody wants to have a go. So what we're going to do is we're going to do this double integral in Cartesian coordinates, and then we are going to confirm the answer by converting to polar. Now, clearly you wouldn't do this in polar coordinates, but it's actually great practice. So let's just have a look what it is. Okay, so we have here our x, y, and we are integrating from y going from 0 to pi, so here's pi and here's 0, and x going from 0 to 2, so here's 2. So we're basically integrating along this rectangle here, and so let's just do it in Cartesian coordinates. So basically that equals, let's integrate y dy first. That is the integral between 2 and 0 of y squared over 2 between pi and 0 dx, and so that equals pi squared over 2, the integral pi squared over 2 between 2 and 0 dx, which is basically pi squared times 2x over 2, which equals pi squared. So it's a very basic, simple double integral, that one, using Cartesian. But what we're going to do is a little bit of fun. We're going to convert it, just to show that you can convert to polar, but it's far, far more difficult. I certainly wouldn't recommend it, but it is great practice for polar coordinates. So what we need to do is, if we are going to integrate over this rectangle here, we need to split it into 2 bits. So I'll tell you what, let's just put the, we're going to put a line there like that. So we are going to split it, and we're going to integrate over the red bit here first, and then we are going to integrate over the yellow bit, and you'll see why we have to do that. Okay, so we're going to integrate over the red bit first. So let's have a look just at the red bit, because we need to get a look at our limit. So here basically is the triangle. Here's the point 2, here's the point pi. Okay, and we're only integrating over the red bit, and then we'll do the yellow bit, and then we'll add the 2 together. So let's take a random point here, r, so that is r there, and here is theta. Now this point here is 2 pi, so we will be integrating from theta equals 0 up to this angle here, which is tan to the minus 1 of pi over 2. So we know that theta is going to go from 0 to tan to the minus 1 of pi over 2. That's theta sorted out. But what about r? Well, we know from this triangle here, and again, let's change the colour, make it a bit easier. So we know from this triangle here, and that's a random point r, sorry, that's a random point r, and here is r here, and we know that this bit here is always 2. So basically we know that 2 equals r cos theta, therefore r equals 2 sec theta. And so we know that r will go from 0 to 2 sec theta. Okay, so that'll be 0 less than or equal to r less than or equal to 2 sec theta. So now we have our limits. Now what we need to do is we need to convert our integral to polar form. Okay, so basically we have the integral of y dy dx. Now we know that dy dx is equal to r dr d theta. We've already discussed that bit. So now our integral will be the integral from 2 sec theta to 0, and that's on the r side, and on the theta side it will be tan to the minus 1 pi over 2 and 0. We've got to be a little bit careful here. Now y, we know that y is r sine theta, that's r sine theta, and then dy dx we know is r dr d theta. So we can integrate the r bit first, so that equals the integral tan to the minus 1 pi over 2. And again, I'm not saying that we should do it like this. I'm just saying this is incredibly good practice at polar coordinates and trigonometry, actually, between 2 sec theta and 0 d theta. So that gives us the integral between tan to the minus 1 of pi over 2 and 0 of sine theta times, just evaluating this bit here, 8 sec cubed theta over 3 d theta. And that equals the integral from tan to the minus 1 pi over 2 to 0. And let's just take the 8 out, 8 over 3, make it a little bit simpler. That equals sine theta over cos cubed theta d theta. So we have to evaluate that. Okay, now just having a look at the differential of cos to the minus 2 theta. Well, that is equal to minus 2 over cos cubed theta times the differential by the chain rule sine theta minus sine theta, which gives a plus. And so therefore we know that this integral here is equal to 8 over 3, 1 over 2 cos squared theta from here between tan to the minus 1 pi over 2 and 0. And we're almost there. Okay, so now 1 over 2 sec theta, that equals 4 over 3 sec squared theta between tan to the minus 1 pi over 2 and 0. And sec squared is 1 plus tan squared, so that's 4 over 3, 1 plus tan squared theta between tan to the minus 1 pi over 2 and 0. Okay, and we are very closely there now, which equals 4 over 3, 1 plus, well, obviously, if theta is tan to the minus 1 pi over 2, then tan of tan to the minus 1 is pi over 2. So that's pi squared over 4 minus 1, which equals pi squared over 3. Okay, so basically the integral just over the red bit is pi squared over 3, and now we've got to integrate over the yellow bit. Now, I never said that it was a better method. It's not. It's obviously not a better method, but it is a very, very interesting method. Okay, so let's have a look now at the second bit of our integral. So let's redraw our triangle. So this is the second bit that we're integrating over now, and that is pi, and that is the point 2. So this is the point 2 pi, and we're going to integrate over here. So now we have to take a random point r here. Okay, so this is theta here, which again by the alternating angle is theta here, and theta clearly in this second part, theta will go from tan to the minus 1 pi over 2, which is where it left off in the previous integral, to pi over 2. That's theta sorted out. What about r? Well, r, if we look at this r here, now we have to look at, let's just, whoops, my apologies, we didn't need that. We didn't need the keyboard. Let's just have a look. So basically r, we're now looking at this triangle here. So r now equals pi cosec of theta from this right angle triangle here. Okay, so now we have r will go from 0 to pi cosec theta. So now we can do our double integral of the second part, this part, and then we add them together to get our answer. So that will basically be on the theta side, tan to the minus 1 pi over 2 to pi over 2. And on the r side, we've already established it would be from 0 to pi cosec theta of, again, r sine theta times r dr d theta. And we can do the r integral first, so that equals the integral between pi over 2 and tan to the minus 1 of pi over 2 sine theta times r cubed over 3 d theta between pi cosec theta and 0. Okay, everybody must be thinking, what on earth is he doing this method? But it is great practice, and that's the main thing as to why we're doing it like this, because it is fantastic practice. And that equals the integral from pi tan to the minus 1 pi over 2 to pi over 2 of, let's have a look, that gives us pi cubed over 3. I'm just putting this into here now. Cosec cubed theta sine theta d theta, which we can simplify as the integral between pi over 2, and let's take that pi cubed over 3 out, pi over 2 and tan to the minus 1 pi over 2 of, well, cosec cubed times sine is cosec squared theta d theta. Okay, now let's just have a look. How are we going to integrate cosec squared? Well, let's just have a quick look. If we differentiate with respect to theta cot theta, which is the same as differentiating with respect to theta cos theta over sine theta, and we do that by the v du dx minus u dv dx, that gives us minus sine squared theta add cos squared theta over sine squared theta, which is minus cosec squared theta, and so therefore the integral of cosec is minus cot. So basically we can go from here down to here, and that gives us pi cubed over 3 times by the integral minus cot theta between pi over 2 and tan to the minus 1 pi over 2. So we're almost there now. So that's minus cot. So basically now we have, so that equals, let's take the minus, that's minus pi cubed over 3, 1 over tan theta between pi over 2 and tan to the minus 1 of pi over 2. And that gives us minus pi cubed over 3, 0, because tan of pi over 2 is infinite, minus 2 over pi, which equals 2 pi squared over 3. So we have 2 pi squared over 3 is this part, and we have up here, where was the answer to that? Pi squared over 3 was that. So pi squared over 3 add 2 pi squared over 3 gives us the total when we integrate over that, add that, is equal to pi squared, which is the same as the integral that we got in 2 lines by doing it with Cartesian coordinates. So you can see you can do these in polar coordinates, and I've got to say I enjoy this one because it is great practice. It really is good practice at using polar coordinates and going through the whole lot. But obviously in an exam don't do that with polar coordinates, and obviously in an exam don't do that with Cartesian coordinates. Okay, well I hope you found this useful. If you have, please press the little thumbs up button and subscribe to the Gresti Academy YouTube channel.